So let's try to get this plasma oscillation frequency by evaluating this double commutator and the second time derivative of this density operator. So last time we tried to evaluate this first time derivatives density operators and the single commutator between Hamiltonian and the density operator, and we cannot get this simple form like this, but this is what we want. We would like to get this plasma oscillation frequency, but from the first time derivative of this density operator, we don't get this. We get a complicated sum over momentum p, and this omega p is not that simple as an independent momentum independent quantity. It involves in this summation over p and all this operator rho, and it's really complicated. So we then try to do it continuously by taking the second time derivative of this operator. So the second time derivative of rho dagger of q, which I use a double dot to represent this double, second time derivatives rho operator, rho dagger operator, q, which is the second double commutator. And the hope is that this can give us, the second order plasma oscillation frequency h bar square omega p squared times this rho dagger of q. Okay, so this is the hope. But by the end of the day, we will show that this hope is really coming true because we can make some approximations so that this prefactor is a momentum independent constant. So the way that we do this is purely by quantum mechanics, that the Heisenberg operator rho of q, or rho dagger of q, is a time-dependent operator. Remember, in the Heisenberg picture, the quantum mechanical operator is a time-dependent operator, and it satisfies this Heisenberg equation of motion. And suppose that this density operator fluctuates in time with a frequency omega p, then we can simply just use this ansatz and plug into the first time derivative of rho or the second time derivative of rho. And if we assume this, which is from quantum mechanics, then we could hope that by the end of the day, we may get the square of this h bar omega p on the right-hand side, multiplied by rho dagger of q. But of course, this is not an easy task because there are many, many terms involving here, including the kinetic energy term and also the potential energy term. And this double commutator is by no means an easy task. But let's try to simplify this calculation and get this approximation down. So let's just try to evaluate the double commutator, which we have done part of the calculation because we have finished the first order time derivative, right? The single commutator between h and rho dagger of q gives me this result. Remember that. And there's no contributions from this potential term because when we sum over p, all these different terms got canceled exactly. So you end up only have this term contribute from the kinetic energy part. But the double commutator, it involves both the kinetic term and potential energy term. But we can take advantage of what we have so far based on this first or a single commutator, and the double commutator now is reduced to that simplified single commutator, right? Because we have already done with a single commutator. So then this is hard work, and I'm just writing down this final expression. Oh, that's really a lengthy form, but plus rho q prime dagger p plus q prime q P, P plus Q, C, P minus Q prime. So it consists of two terms. One is the second order in this energy difference from this kinetic energy term. And the second term, I mean this cross term between the kinetic energy and the potential energy term, because it carries this energy difference that comes from this kinetic energy term, but we need to multiply this by V of Q prime, which is the potential term. And all this kind of operator, C dagger C minus C dagger C multiplied by rho dagger, they all come from the potential term. So it is a mixed, the cross term between the kinetic energy and the potential energy term. Sorry for that, but this is, again, once in a lifetime homework. For experimentalists, prove this and derive this double commutator. For theorists, it is a necessary exercise. So you simply just evaluate this commutator, and by, again, repeatedly applying, taking advantage of this anti-commutation rules between fermion operators, and you could simplify this commutator up to here. So let's just call this purely connected term the first term, and the cross term second term. And let's try to simplify these two terms. The first term is the second order in this energy difference between the single electron connecting energy, and this is given by sum over P 2 times P dot Q plus Q square, and everything square, C dagger P plus Q and Cp. So this is the order of Q square plus the term order of Q quartic term. And we know that in this small momentum transfer limit, that Q goes 0, and so this term is really, really tiny. So we try to neglect this term, but we need to explicitly write down the condition that we could do that. So you could show that this leading term is probably given by h bar to the fourth Fermi velocity square and Q square and rho dagger Q. Because if I simply just neglect this Q to the power fourth, this is the even higher order term, and I only keep this P dot Q term and I square this. So this is given by P square Q square, but P is very close to the Fermi surface, which is close to the this Fermi momentum. So we could convert this P square to this Kf square, and we could divide this by this kind of, we could convert this Kf over m into the Fermi velocity, and this is approximation. H bar square P over m is approximately given by H bar square Vf. So this is the first approximation, and because we know that close to zero temperature, all these active states are the states close to the Fermi momentum. So the P summing over P, the momentum, is actually very close to this Fermi momentum. So we can make such approximation. So therefore, the leading term is given by this, and we try to neglect this term. So, but how so? Suppose this is really, really tiny. This is really, really small, and we assume that this quantity is actually much smaller than h bar square omega p square. Or this Vf square Q square is much smaller than omega p square divided by h bar square. And we know that on the right-hand side of that double commutator, this is h bar square omega p square, right? Okay? So, but the first term on the right-hand side is given by this complicated terms, like this term. Suppose that the Q squared term from the pure connected term is much smaller than this h bar square omega p square. Then we can safely neglect this term, right? But this is a big if because we need to justify this. So, but that can be done later, this approximation. After we throw away this, and we could get this omega p as we like, and we know this value of omega p later, and then we could go back to this approximation and see if this approximation is valid or satisfied or it is reasonable. So we will go back here again, but here allowed me to simply just forget about this term altogether because it can be really, really tiny compared to this omega p squared. Okay, so that's pretty easy approximation. It's easier said than done, but we need to justify this later. But we postpone this justification at a later time. Okay, so let's take a short break. When we come back, we will continue analyzing the second term. For this part, please read David Pine's book and also Kittel's second book, Quantum Theory of Solids, and also Flansburgh. Especially David Pine's book is really a nice reference, and he explains this kind of a density operator pretty well. And I think this book is his lecture notes. It's probably written in 1960s, no later than 1970, I'm sure. Okay, so you can see that this kind of theory was already established very long time ago, and it constitutes a standard paradigm for theory of metals. So now let's throw away the pure connected term, and we could complicate it. We could play some trick by shifting the momentum variable p to p bar plus q. Okay, so for the reason that will become clear later. All right, so because p is any arbitrary momentum variable to be summed over, and I could simply shift this p by small momentum transfer q, and I call this shifted momentum p bar. And p bar is also arbitrary because q is just a small momentum transfer. I could just subtract this or add this q as I like, because both p and p bar are simply just arbitrary momentum. So if I shift this p, and I can sum over p bar and q prime, bq prime over 2 plus q dotted q divided by m, and multiply by this complicated terms. So let me just p bar plus 2q minus q prime bar plus q and rho deg q prime plus rho q prime p bar plus 2q minus q prime bar plus q, and minus another 2 plus 2q bar plus q plus q prime rho dagger of q prime plus 2q bar plus q minus q prime and rho of q prime. Okay, so it looks horrible, but later you'll see that after some simplification, this reduces really elegant form. Okay, so the reason why I'm doing this shifts is precisely because remember this p dot q term involves sum over momentum p, which complicates the sum. So I could simply shift this p to p bar plus q so that I can isolate this q square, because I know that this q square term plays an important role. And this p bar still needs to be summed over, but we will do that later, right? We should extract this q square term first. So let's try to look at this q square term. You could simply apply the definition of rho dagger of q, right? So this is sum over p, c dagger p plus q, cp, right? 1 over volume. So use this definition, and remember, if I single out only this q squared term in the prefactor, then the summation over p bar will only involve c and c dagger. So that this has nothing to do with this term, q squared. So that I can safely just move this p bar summation into that big bracket so that I can use this definition. This is my motivation. Okay, I would like to make this C dagger C operator rho dagger of Q or rho dagger of minus Q as much as possible, because we know this is the unit that we like to group together. So after all, this is the density correlation. So it should have this term that there are two density operators here. Okay, but there's only one here. So we could intentionally make this C dagger C as some other density operator. Okay, so that there are two density operators here. So this is precisely the second double commutator is given us. So it is proportional to rho Q squared. So there is just one row, but there is another row, which is here. So that we should shift this momentum P so that we could single out this Q squared term. And later, we will argue that this P bar term multiplied by all this complicated C dagger C with the summing over P bar, they will become very, very small, and they could simply just be neglected. So we will see that later. So let's just combine this Q squared term first. And from the definition of this rho of Q, we immediately see this VQ prime over 2 H bar square Q square over M rho Q prime minus Q rho dagger Q prime plus rho dagger minus Q prime rho minus Q prime and plus summing over P bar, complicated function of rho Q times C dagger P bar plus 2Q Q prime C P bar plus Q, something like this. Okay, so we can simply just single out the Q squared term. And the Q squared term can be expressed in terms of rho and rho dagger operator like this, because we could take advantage of the definition of rho dagger of Q. So we sort of convert the C dagger C into the density operator rho. So this is the magic. And we sweep all the other terms under the carpet in the second term, where we have double summation over P bar and Q prime, right? So all the other terms are here. But we will argue later that all these terms is actually very, very small. And the reason will become clear later. But let's just group together the first term, simplify this term. So the first term gives you some finite contributions only in these two cases. The first one is when Q prime is the same as Q. The second is when Q prime is minus Q. So in other words, this term will lead to some sizable contributions only if one of the rho is actually rho 0. It's the Q equals 0 component of the density operator. So you see that when Q prime is actually the same as Q, so this first row is actually rho 0. But what is rho 0? Rho 0 is nothing but the average density, right? Which is huge. So the leading term is always rho 0. So remember this RPA, the random phase approximation. So we have this rho 0, which is the average density. And rho of Q, where Q is non-zero, shows much smaller amplitude fluctuations than rho 0. It's a constant background. So that your density profile in terms of the distance is actually constant average plus some small fluctuations. And this constant average is nothing but rho 0. And this finite Q component of the rho stands for all this density fluctuations. And we assume this density fluctuations, which is a finite Q component of the rho of Q, is much smaller than rho 0, which is the average density. So just look at this picture. The rho 0 is the leading term, and rho of q is a subleading term. So we can throw away the subleading term by keeping only rho of 0. Okay? And that's why we need to consider only these two cases. The first case is when this term becomes rho 0. The second is when this term becomes rho 0. So this is really important approximations, which is a reasonable approximation because that approximation is confirmed in many experiments of metals that rho 0 is just a constant background uniform charge distributions, but on top of that we have small wiggle and oscillations of charge density, and so that justifies this approximation. So we just take these two limits or two cases, and so that first term now becomes the following. Of course, this is approximation, q squared over m rho 0 rho dagger of q. The second term rho dagger of q and rho 0. So by considering these two cases, we sum over q prime, so that's when we have contribution only when q prime is either equal to q or equal to minus q. So we get rid of this q prime summation, and therefore there's no summation here. There's no summation. So now you see the magic. Because rho 0 is just a constant, independent of anything, but it depends on the mass and this density of electrons and so on and so forth. But it doesn't depend on q. So what is VQ? Well, VQ is nothing but the Fourier transform of this Coulomb potential, which goes like 1 over q squared, right? So this goes like 1 over q squared. But there's a q squared in the numerator. So this q squared will certainly cancel with the denominator of q squared, so that the whole thing is independent of q. So that's the magic. So let me just organize this term. This is 4 pi e squared over 2q squared times h bar squared q squared rho 0 divided by m times 2 times rho dagger of q, which is 4 pi e squared rho 0 h bar squared over m rho dagger of q. And remember, this is double commutator, right? Which is supposed to be h bar squared omega p squared rho dagger of q. And the thing inside the yellow box is precisely h bar squared omega p squared. But down. So what is omega p? Where omega p squared is 4 pi e squared rho 0 over n. So we have successfully extract this plasma oscillation frequency omega p by making some approximations and neglecting many small terms. But let's just go back to this approximation here that we neglect this the other term. So what's the argument? Well, the argument is precisely this RPA. Remember, as I mentioned, this is really a complicated summation over rho and c dagger c, but we know that these c dagger c cannot be reduced to rho 0. So these c dagger c is actually the order of rho of q, or q bar, or q double prime, something. So the important thing is that the rho of c dagger c here is actually proportional to the finite momentum component of this density operator. So that all this complicated summation over p bar is actually at the second order in density operator. So remember, this is the whole thing is actually second order in density operator. But if we extract this rho 0 from here, then this the first term is actually the linear in density operator rho of q. Okay, but the second line here is actually second order in rho of q, because this c dagger c operator cannot be reduced or simplified to this rho 0. It has to be the function of rho of q, or a complicated combination of rho of q, so that you get 2 rho of q. And by RPA, rho of Q is much smaller than rho of 0. So this is, again, higher order compared to rho of 0. And that's why we are allowed to simply neglect the second line, because this is higher order. Of course, this is not the exact result, because, of course, this term will contribute something, but that something is too small to be included at the leading term. So up to leading term, we throw them away. This is justified. So, of course, this is not the exact relation because we already throw away something which is small, but that approximation makes sense under RPA. So we are allowed to make such assumptions, and not assumption, but approximations. Good. And so this allows us to work things out, and omega p can be obtained. So you can see that plasma oscillation frequency depends on electron mass and also rho 0. So the higher density, the higher the frequency of oscillation. Okay, different metals shows different plasma oscillation frequency. Well, so that's one thing. Another thing is, let's just look at this assumption that we make, that Vf squared Q squared has to be much smaller than omega p squared divided by h bar squared. So since we know this omega p squared, so let's check whether this kind of approximation is valid or if this makes sense or not. Okay, so let's just plug in this omega p, which is this value, and we could really see whether this approximation holds. And suppose Q is really small. Q goes to 0. And we know that rho 0 is actually a huge number in ordinary metals. And all this h bar squared m is just a standard universal constant. So as long as Q is small enough, this inequality is always satisfied. So this could be satisfied easily. And that justified the approximation that we made earlier by neglecting the kinetic energy term, right? So as long as Q is small enough, then we are fine. Of course, this is, again, approximation because we neglected all the pure kinetic term. But again, so in the limit of Q goes 0, this approximation is okay. Therefore, so let me just make this physical picture more clear. So we have such density oscillations in solids, and we know that this is just a collective motion, right? So this is kind of collective motion back and forth with the omega p, which is given by this rho 0 over m, some prefactor. And this is a many-body phenomena. So we could very clearly see this is many-body phenomena because of this. Remember this. So this electron density operator in momentum space, and also at the finite Q limit, where Q is actually small. And this kind of a small fluctuations in density of electrons is actually a periodic motion in time. But what is rho of Q? Remember that. Rho of Q stands for this kind of a particle hole excitations, right? K and K minus Q. So you sum over all possible electron hole pairs near the Fermi surface, and that defines rho of Q. And therefore, this kind of a density operator, rho of Q, involves everybody close to the Fermi surface, right? So you need to sum over all possible electron hole pairs near the Fermi surface. And those electrons as a whole, right, dance together in a characteristic frequency omega p. And this is the meaning of a collective motion, because this motion is not just for a single electron, but all the electrons close to the Fermi surface that will lead to some small momentum transfer electron hole pair excitation. So all such electron hole pairs actually dance together. So they dance together in a characteristic frequency omega p. And this is something that cannot occur in classical electrodynamics. So for electrons, in a classical picture, we cannot imagine that those kind of electrons can know each other and can dance together. And this is purely due to many-body quantum effect. So it's a quantum mechanical effect for sure, because we evaluate Heisenberg equation motion, but more importantly, this is a many-body effect because it involves all the electrons close to the Fermi surface. It's not just a single electron dancing, but everybody is dancing together in the same frequency. Okay? So this is the first time I think all of you understand this quantum many-body phenomena. So the plasma oscillation is the classic example of a quantum many-body effect. I guess time is up for today, but we will finish this by making some remarks on plasma oscillation frequency and this physics. Remember, we have this small momentum transfer physics, which is the plasma oscillation. We also have a large momentum transfer physics, which is a single electron-hole pair excitation. So we will link these two phenomena together in the next lecture. So have fun and try to understand this physics in terms of the many-body quantum phenomena. Okay? So it's not easy to understand this physics without using second quantization formalism. Think about this. If you don't know about this C or C dagger creation destruction operator, can you understand this? So that's the real test. And you go back to the Ashkenazi or Kittel's introduction to solid state, where they don't introduce this second quantized fields, and just look at the chapters on plasma oscillation and see if you can understand. Or they provide, the full understanding of this phenomena. I think the answer is no. So we need to rely on this kind of electron destruction and creation operators.
I think the current result is the same as those in the Ashkenazi chapter 1 about the Drew model. Use a kind of semi-classical.
Right. So they use semi-classical. So they can sort of understand to some extent. However, they have trouble understand the rest of this phenomena, like electron, dielectric function in solids as function of frequency and momentum transfer. That is a part of this plasma phenomena. And of course, they can understand up to here, but there's no way that they could get this full picture of this dielectric function as function of a momentum transfer and omega, which could be studied experimentally in this optical absorption of your metal.
And my second question is, it seems if we found the Ashkenazi, it seems the electron collected motion in the real space, but if we use your particle Hall picture, it seems like oscillation in the K-space. Can I say this?
Yeah, of course. In Ashkenazi, so this kind of fluctuations, I'm not sure if they can capture this frequency. Of course, but semi-classically, so that they should miss something quantum mechanically. I have to check what they missed if they simply just use semi-classical picture to capture this. Okay, so the second question is the real space of moments. Of course, this is a Q-space physics, because you know that those electron-hole pair near the Fermi surface, when they are formed, they should carry this momentum transfer. So by Heisenberg uncertainty relation, if you know this momentum, do you know where they are? No, that's right. You don't know where they are. So the correct language should, of course, be in the momentum space. And this is precisely what you will see. You don't know where they are, but you know their momentum. And this is what we call the density fluctuations. You don't know where they are, but they are very close to the Fermi surface, and they have a very small momentum transfer. Okay, so that's the real picture. You don't know where these electrons are. They may be far away from each other, but they are close to the Fermi level, and they have a characteristic momentum states and momentum transfer. So that's the correct way of looking at this plasma oscillation physics. Always thinking about this in Q space and in time. Good question. Okay, so I'll see you next Monday.